To keep the global economy moving, millions of heavy freight trucks and city buses run on our roads every single day. We're talking about machines hauling up to 80,000 pounds across continents, or navigating hundreds of congested city intersections. Replacing all those diesel engines with batteries hits a massive physical roadblock. To move that much weight over long distances, you need an enormous battery. These units are heavy, they take hours to recharge, and they eat directly into a truck's cargo capacity. This chart maps vehicle weight against required range. While lightweight passenger electric vehicles work well in the lower quadrants, heavy loads and long distances push us into a dead zone. Here, the required battery weight becomes mathematically unviable. Supply chains need a way to generate massive power without relying entirely on the electric grid. The solution to this everyday infrastructure problem is coming from an extreme environment: Formula One. The engineers designing cars to hit 200 miles per hour have spent the last decade figuring out how to squeeze the absolute maximum power out of every single drop of fuel. Their work provides the exact blueprint needed to decarbonize the city bus and the logistics truck. In 2014, Formula One overhauled its engine regulations, scrapping the older V8s for smaller 1.6-liter V6 engines. These new units were paired with complex hybrid systems and exhaust superchargers. This forced engineers to focus on thermal efficiency, the percentage of energy from fuel that actually moves the car. This visualization shows the old standard. V8 racing engines had a thermal efficiency of about 30%. The other 70% was wasted, bleeding out as pure heat. By capturing that lost energy, modern F1 engines have pushed past the 50%. This makes the modern Formula One power unit one of the most efficient internal combustion engines on Earth. It is a high-performance hybrid template for moving heavy weight. One of the primary tools used is the MGUK, or Motor Generator Unit Kinetic. This component harvests the energy usually lost to the brake pads during deceleration and converts it into electricity. Public city buses perform constant stop-and-go driving. This makes them the ultimate generators of wasted kinetic energy. Years ago, F1 engineers developed early flywheel-based kinetic energy recovery systems. That technology was adapted and integrated directly into the power systems of London's iconic red buses. By capturing that kinetic energy and feeding it back into the drivetrain, city transit becomes significantly more efficient with every stop, turning the act of braking into a fuel-saving mechanism. While buses deal with stop-and-go traffic, long-haul supply chain trucks face a different challenge: constant heavy load demands for hundreds of miles. To solve this, F1 uses an MGUH, or Motor Generator Unit Heat. This unit captures searing waste exhaust gases to spin a turbocharger and generate electrical power. This exact process, called turbo-compounding, is being applied to heavy-duty commercial trucks, like those from Scania, to recover energy from their massive exhaust systems. These heat utilization systems are integrated directly into the truck's powertrain. Waste heat from the engine passes through a heat exchanger and an expander, converting thermal loss back into mechanical work. This chart shows the result. Recovering this heat translates to a 4 to 7% savings in fuel. On the scale of global shipping fleets, mastering these recovery systems essentially turns the exhaust pipe into a secondary power source, recouping energy that has historically been considered lost. Formula One applies this technology to its own enormous, globe-trotting supply chain, which must reach net zero emissions by 2030. Their strategy includes the use of sustainable aviation fuel certificates and a transition to biofueled heavy transport trucks for their terrestrial logistics. Recently, teams had added fully electric trucks for European routes to complement the biofueled fleet. The sport operates as a real-world stress test, proving that hybrid efficiency and biologistics can successfully sustain a massive global operation. While pure battery electric power is one solution, F1's data suggests that advanced hybrid internal combustion remains a necessity for heavy-duty transit. By 2026, the sport will move to its next frontier: 100% synthetic e-fuels. This creates a closed-loop system. Carbon is captured from the air to manufacture the fuel and then released back into the atmosphere during combustion. No new carbon enters the cycle. The engineering that shaves milliseconds off a lap time provides the gritty, efficient foundation for the future of our cities and global supply chains.